Okay, so let's talk about solving this example 1.2. First of all, let me mention that this is solving an initial value problem, IVP. And we do that in two steps. So the first thing we do is we solve the ODE, and then we apply the initial condition. So let's do those two steps now. All right, so the first step is to solve this first order linear homogeneous ODE. To do that, we are actually going to bring it out of its standard form. And we are going to put the term with y on the right-hand side. And then we're going to divide by y so that we get all the y's on the left-hand side and all the t's on the right-hand side. Later on in lesson 2, we'll see that this is kind of what we do if we want to solve this as a separable ODE, and that's coming up next. So at this point, we can take this and try to integrate it. So we're going to integrate both sides with respect to t. This is where I want to pause the writing and mention that at the very end of the lesson notes, there is an integration table. So this has most of the common integrals that we are going to be using. And I've already highlighted one here that we're going to need in a minute. So antiderivative of cosine u is sine u. So I definitely recommend that you go over this integration table and try to find ways to commit those to memory. So there we are, about to implement that antiderivative of minus cosine t is minus sine t plus c1. So I put a 1 down here because we're also integrating on the left-hand side. That is going to trigger another arbitrary constant. We will call that c2. So I just wanted to distinguish the two in a minute. So the left-hand side integral, though, is a little bit trickier. And the reason is that, there's just a lot of stuff going on here. So we're going to make use of a little factoid from calculus. So let's talk about what that factoid is. So here is what we're going to try to do. What if we differentiate the function ln of y of t with respect to t? Well, so here y of t tells us that y depends on t, but we don't know how. So this was called in calculus an implicit function of t. Implicit because it's not explicit. If we knew that y of t was t squared, then we could just plug that in here and then differentiate with respect to t. But we don't know what y of t is because it's inside this ODE, and that's actually what we're trying to find, y of t. So to differentiate with respect to t, we can use implicit differentiation. It's basically an application of the chain rule. So what we do is we differentiate with respect to y first, and then we multiply by the derivative of y with respect to t. So the derivative with respect to y of ln of y is 1 over y. So then we have this little factoid, which is what I mentioned earlier that we will use from calculus, that the derivative of ln of y of t is 1 over y dy dt. Great, so if we scroll up and we look at where we were in our intermediate steps to solving the ODE, we had on the left-hand side this antiderivative left to do. And there is the 1 over y dy dt that we can now replace with this d by dt ln of y of t. So that's what we're going to do with the left-hand side. So we can go back to the left-hand side and write this as integral of d by dt of ln of y of t. And on the right-hand side, we had already integrated that to sine t plus c1. Great, and now you might remember that the integral and the derivative are operators that undo each other. So if we integrate the derivative of something, we just get back that something. And again, we're integrating indefinitely, so we get another arbitrary constant. So we'll call that c2. Great, so then here we are going to combine c1 and c2 on the right-hand side. I'll just subtract c2 from both sides, and I'm just going to call the result c. So this is one thing that I will do in general. You'll see me do this throughout the course. Whenever we have two indefinite integrals, I'll scroll up here to show you where they first started or originated from. Here was one, here was the other. Each one of them is going to generate a c. And in general, will combine them into just one arbitrary constant on the left-hand side, sorry, on the right-hand side. So again, you'll see me do that a lot throughout the rest of the course. Great, so here we are. And to solve for y, we exponentiate both sides. And that leaves us with e to the minus sine t plus c. I'm going to split this up a little bit to make it easier to apply the initial condition in a minute, using properties of exponents here. And then I'm going to call e to the c this new arbitrary constant, k. All right, so this is the intermediate form of our final answer. We don't yet know what k is, and that is something that we're going to pin down now by applying the initial condition. So let's go up and figure out what the initial condition was. So here the initial condition, we're back to step 2 now. Y of pi over 2 equals 2. Great, so let's go down here to step 2 and apply that. And we can do it in this little part over here on the right. So step 2, apply y of pi over 2 equals 2. Okay, so to do that, I'm going to say 2 equals y of pi over 2, and then I'm going to use the y that I have, which is k e to the minus sine t. And we are plugging in pi over 2 in then for t. So I plugged it in there. Great. And then I have to remember a little bit of my trigonometry here. Sine of pi over 2 is 1. So this is k over e. So I have this simple equation, which gives me that k is 2e. Great. So then I'm going to go back to my final answer for y of t and put that in as the k value. So I have 2e times e to the minus sine t. That is the final answer, the final solution to the initial value problem. But if you want it a little more simplified, just a tad, you can combine this hidden 1 up here with the minus sine t and make it 1 minus sine t. And that is our final answer. Quick little comment about this. You notice that there is no k in this answer, whereas over here there was a k. Right? And that's again because this is pre the initial condition, and this is post the initial condition. So again, if you want a unique solution to a first order differential equation, applying the initial condition gives you that and eliminates any possible plus c's or plus k's or whatever the case may be. Great, so that is the end of this example.